Example 2, we're going to sketch the graph of y equals 6 over x minus 2 minus 3. So this has a vertical stretch of 6, so we're going to do our counting with the 6. This would mean that it goes right 2, and this is down 3. So I'm actually going to draw my asymptotes first, because if I went right 2, that means my horizontal asymptote, or sorry, my vertical asymptote at x equals 0 is now at x equals 2. So I'm going to draw on those asymptotes. Down 3 would mean that my horizontal asymptote has shifted down 3. So we're at y equals negative 3. So the reason I draw my asymptotes in first is because this allows me to treat this like a new x and y coordinate. So that's where I'm going to do my counting from. So then I count using the a value of 6. So if we have a is equal to 6, that means from here, I can't count on here. I can count along the asymptote if you want. 1, 2, 3, 4, 5, 6, but it's got to be 1 up from there. And then here, same thing. You can count on the asymptote. 1, 2, 3, 4, 5, 6. Of course, the point's not on the asymptote, so you can go here. I usually just count within there. And you've got your 2 points. Now, I would say that you would want to make sure we're going to have a clear x-intercept so that we find that. And I would also then maybe just test another point. So rather than do a full table of values, I want you to just think about what the graph was when it was y equals 6 over x and choose a value that would be nicely divisible by 6. So you can choose 2 or 3. So for example, if I chose 2, this is 3. So that means that as if this was my new x-axis, I would plot x equals 2, y equals 3, and I actually got lucky that that's my intercept. We'll confirm how to algebraically find that too. So I've got some points there. If you wanted to, just because this is such an easy one to do, it's divisible by 3. You can see how if you went 3 and 2, and again, now I know this is the point 5 and negative 1, but I'm just counting as if this is my new origin, because in my work here, I wasn't putting in the shifts. So it's so much easier just to think about those points. So we've got our curve here. And so down here, we're going to just mimic that. This is going to be 1, 2, 3, 4, 5, 6. And this is going to be 1, 2, 3, 4, 5, 6. And again, I know that we had the point when I chose 2. So we went 2 and then 3. And again, I got lucky and actually have an intercept there. And I also went 3 and then 2. So I've got lots of points on this one. And we'll curve that one there. So I just want to algebraically show you how I would find the x and y intercepts as well. So I'm just going to kind of make some more room for myself here. So let's say I was finding the x-intercept algebraically and I didn't even have the graph. If I have the graph and it happens to be a perfect integer number, then great. But otherwise, we would let y equal 0. So I'm putting 0 into the equation. So I just want to make sure the algebra is there. You'd move the 3 over. You would cross multiply or multiply both sides by x minus 2 to clear the fraction. Either way, you're going to get this in your next step. Multiply the 3 through the brackets, or in this case, you could actually divide off the 3, but if it wasn't divisible, this is going to be probably a more often situation here. Move the 6 over, so I get 3x equals 12, and I've got x equals 4, so that confirms that. My y-intercept, you let x equals 0, so y is equal to 6 over 0 minus 2, then minus 3. So y equals 6 divided by negative 2. So you get negative 3 minus 3. So y equals negative 6, which is also true. So if you're not given the graph, that's how you can find your x and y intercepts if you're just given the equation. Or if your intercept is a fraction, for example, which is going to happen often, and you can't clearly see for sure what it is on the grid, then you can find it algebraically as well.